So we're going to talk measurement errors found and fixed. Learn the rules like the pro so you can break them like an artist. You guys can hear me good still? Everything sounds normal? Hopefully. How am I doing, Mark? Thumbs up, thumbs down? Thumbs up? Okay.
Good.
Okay, good. Learn the rules like a pro. So if you guys stick a thumbs up, I can probably see it, but I can only see a few at a time, so I might miss it. Anyhow, we're going to go through this class. At the end, we'll have a few minutes for some questions as well. I'm thinking it's going to be, overall, this class is going to take 45 minutes or so, and then we'll be done. So we'll do about 45 minutes and then 5 minutes of questions. And as soon as the questions are over, then we'll continue. So welcome. And here we go. It's a virtual training, so I asked that we'll rename our screens. You guys did that. If you want to put your first name and company, that would be good. There's a quote here we're going to sort of talk about. Daring ideas are like chessmen move forward. They may be beaten, but they might start a winning game. And some of the ideas I'm going to put out here, we might argue them. We might think those are bad or wrong, and we might have some different ideas, but we're going to discuss the ideas, and it'll, sort of like a chess move. There might not be the right one, or they might not be the only one, but these are the things we found, and we'll learn from them. And there could easily be other things as well that we can add to it. Some of the items we're going to discuss today are a water cut analyzer that was accurate at 12 degrees Celsius way out as soon as it got to 11 degrees or below, right at that gripping point at 12 degrees or 11 degrees is where it changed. A Coriolis meter, it passed verification, but was incorrect in density and volume. We're going to talk about some fresh water in their emulsion, how that gave them an incorrect water cut. Another thing is we're going to talk about two identical meters opposite end of water lines. There was about 7% different. We'll talk about a Coriolis meter. It had a 6% change in it, and it was the Coriolis line balance meter. We'll talk about some of our F series. I'm going to put my little tracker so you can see me better. We're going to talk about some of the F series meters, like this one in the middle of the screen on the bottom, and how we found some errors in them just lately. There's quite often density errors in those, and we'll talk about that. And then we'll talk about our dump valves that are passing. We talk about that at the end, and the reason I talk about the dump valves passing and I want to put that in is because it's the single biggest error that we find, the single most common error we find that affects the measurement, and we find it probably more than any others. In fact, when we look at the numbers, about 10% of the proofs have that, and about 6% have some other thing altogether. So it's probably twice as common of a measurement issue as anything else that we see. So we'll talk about those. So we'll start our phase dynamics. One of these phase dynamics water cut analyzers, it verified just fine in the fall, but in the winter there was a huge error. And we kind of wondered why. So the way we do these calibrations is we basically take samples. On this one, we did 4 different samples. You see what the analyzer is reading. Well, you take your sample, you heat it, you spin it out, you get a sample cut, and you see what the difference is. And so normally, these are a fairly accurate analyzer. But on this particular one, we saw it was 64% is what the analyzer read. The sample cut was 55%. And so it was reading about 8% extra water. And we did it at some different percentages as the different production came in. And all of the differences were between 8 and 16%, always reading. There was the analyzer was reading high on this one. And so we thought it's always reading high. There was a code in it, if you went through the codes, it said salinity overrange, a code 22. And so we attempted to calibrate this. The way you calibrate it's, I'm not going to go into that right now, but it's use a data phase water capture, or water phase data capture. And when you do that, normally that captures it, it fixes it. But there is still a calculation overrange. So how can you tell the calculation is overrange? Well, in the programming of these, if you can see on that, it'll show water cut. There's different screens. It'll go water cut, temperature, and the oil. And the next screen, there it is, salinity. You get to one of these screens, it shows their salinity is, and it'll show the salinity range on these, which is 8% is the high end, the minimum is 0.1, and it's set at 8.00. So that ended up being that ended up being a clue to us. It was set at the highest number that it could be, 0.1 to 8, and it's set at 8.00. So what we ended up doing with this unit is getting the factory engineers at Phase Dynamics to model it. And they checked all the calculations. They found that it would read high if the water cut temperature changed below 11 degrees Celsius. When they first did it, everything worked perfect on it, they said, and there was nothing that was out of order in it at all. Everything was working perfect. And then he says, well, wait a minute, I'm at 15 degrees Celsius. What's your temperature there? And when we told him that it's running at 4.2 Celsius, he couldn't believe it. They're from, I think, Texas or California. I'm not exactly sure where they are, but they're southern United States anyhow. And he couldn't believe that we would have any oil like that gets that cold. And we're like, well, it's winter time and it's Canada and it's cold. And 4 degrees C is really not uncommon at all. Lots of times it's probably below 0 Celsius or shipping tanks. But there was that error and it might affect others. So what we had to do to fix this is the factory engineers built new internal tables for this. We had them to make new salinity tables, a new configuration file. We upload the new configuration file into the unit, and then it went from 0.2 to 11%. And the actual salt content here was at about 10%. So when we were running with 8% as the maximum, it was just off of their internal table, their internal scale. Once the scale went higher, the numbers were on the scale and it all worked just fine. To verify, we did as well 3 more samples, and the samples, the oil, we got at 88%, 88.3 is what our analyzer read, and our sample read 88.5, 0.2% difference. We did it a few different, and all the samples are 0.2 or 0.3% from the reading, so it was all within their 0.5% tolerance. So what did we learn from this? You need to watch out for settings that are at the very end of their range. When it says 0 to 8% and it's at 8%, it might be at 8%, but it might really be at 10%, as this was. And when you're working on a setting that's on the end of the range, you really don't know if you're at the end of the range or off the range, as in this case, off the range. So watch out for that. And my COVID joke for the day, seeing how we're all locked down from this COVID, I wrote a joke about COVID and no one got it, but eventually everybody did. Okay, that's as good as it gets. Okay, next is we have 2 different Coriolis meters. They both had similar issues when we found it. We attempted the first ones that we're going to talk about. Let's see, I don't have a picture of the first one, but we attempted. It's a 2-inch Coriolis sales meter, and the as found runs, they showed a large error in reproducibility. The run meter factors from 0.95 to 1.014 or something, so about 7% difference between runs. And we found that the densities were reading off and the flow rate was very incorrect. Everything looked good on the programming and it passed meter verification. So here's part of our proof report. There's a whole bunch of details. The important numbers on the bottom in this yellow tell sort of the average. The average meter factor is 0.98. But the run repeatability is the one that is horrible. 7% between runs when we did this. And it's a Coriolis meter. It's got the software that you pay extra for, so you can do the electronic verification on it. And so we do the verification, and several times it passes verification perfectly. Yeah. So it's going through the verification just fine. Yeah, there should be okay, so it's working good there. We got the operations though to schedule a cleaning. We thought maybe there's something in the meter, that's possible. So we got into schedule of cleaning or something in the meter, something lodged in it. And what we found out is the meter was clean, it was totally free of debris. We sent it to the manufacturer, and on this, one of the parts had come loose inside, so they had to take it apart, cut it open, glue the little sensor back onto the tube, and it was all good. But it was one that passed verification multiple times and did not pass approve, 7% error. So that was something they don't always, just because it's got verification software and it passes, doesn't always mean it's working. The second one we do have a picture of. This one passed verification. It's the triangular shape Coriolis, a 1 inch. On this, the problem was reported that the water cut was way out. So we thought the issue could be the sensor tube itself, something in the sensor tube. It could be in the core processor, which is in the little box attached to it, or else in the transmitter, or the FlowBoss 107, or the rock knock that it goes to. So on this, what we did is we connected to the transmitter with the software, and it showed a whole lot of alerts on this one, a whole lot of errors. And it's not uncommon to see errors when you connect because they store them for a long time. And if there's a power failure or different things, you'll get some of these errors. But it did have some that we didn't like. The density overrange, some of these errors are really normal. Density overrange is normal. If it ever goes through, it's warning you. Transmitter warming up or transmitter failure, you quite often get those from a power failure as well. Insufficient pickoff signal sensor failure. There's some here. You don't usually see them all, but you do see them. So we performed a data log for a while. I thought, let's see what this thing is doing. So we wanted to see what is showing for density and what the real measured density is. And so we data logged it for quite a while. And what we found during data log is the Coriolis would show like a density 0.96, 0.97 kind of density. The temperature was 5.7, the drive gain 47, which is really high. This is a pumped liquid meter. Usually a drive gain is like very low, under 10%. The flow rate was a decent flow rate on this pumped meter. On the FlowBoss, we found the same numbers. So the numbers calculated out what they should be on the FlowBoss. And our measured density was actually 1.05, 1.06, and water cut should have been like in the 90% range, not the 40% range. So to do troubleshooting, we disconnected the core processor from the transmitter. We powered it with a portable power supply. And some of you guys are more techie, and I know there's lots there that are listening with Ben. You can check the transmitter and everything by just totally disconnecting and powering the core processor directly with the correct power. It's about 12 volts, it's got to be above 11.5. So a battery from a cordless drill works great. And then it's not a transmitter or a power supply or anything else because you can totally eliminate everything else from the system. But with that, we performed meter verification. The meter still passed verification, but it still had those same density errors. So we did some more troubleshooting, consulted with Micromotion, and what are the other possible checks? What did we miss? And they suggested there could be a soft wax coating. So that was the only thing they thought it could be. We kind of thought it might be something in the electronics, the core processor, but we weren't really sure why. So we pulled the meter, and there's two tubes in these. There's a tube in each side. And we pulled through the meter a rag, like a really tight cloth, a cleaning cloth through both of the tubes. It came out absolutely clean. There was no debris, no wax. Everything looked good. So we weren't sure what it was. We did a temporary fix just to see if we could make an adjustment and make it sort of work. We did that with a K1 with an air calibration, and K2 we adjusted till it got the correct density. And so we sort of did a temporary fix that's not really right, but it sort of is a troubleshooting temporary fix. And then we took the emulsion samples after a temporary fix and measured the water density and the oil density and everything. Once we temporarily fixed it, it was sort of close, but still a huge variance between runs. We did 2 more meter verifications after this with a temporary fix, and it didn't work. But between runs, we still had 6% variance. our average was really close to what the average should be. So we thought, well, it's in the ballpark, but you can't leave it with 5 or 6% variance. So ultimately, we pulled the meter out and had to do some shop repair work on this. And so we put the numbers back to the factory settings, and it showed exactly like it was in the field. The Coriolis density is reading about 0.91, 0.92, and really in the shop was 99, just about 1, fresh water. And our drive gain was still in the 47 to 50% range. So there's still problems as received in shop. So what we did then is we pulled it apart, or we put a borescope through, and we found that there was about 12 inches clean on each side. So in this meter, it was a triangular shape, and there's 12 inches of clean, and then it went to like a black plastic coating. It just looked as though it was painted. And so the bottom section was totally coated with a black plastic coating. And we weren't really sure how to get these, but Coriolis, the standard temperature they're good for is about 240 Celsius or so. So we thought we'll just heat it up and see what happens. And when we heated it at about 50 degrees Celsius, it turned soft, and 65, it just turned to a liquid. So we just tipped it upside down, turned it out. And as soon as it hardened on our cloths, it just is a black plastic is what it looks like. It melts about 65 degrees Celsius, it cools off, and it's black plastic. But after we got it out, we checked with borescope, then found the tubes all the way clean throughout. We again did a prove right after cleaning, and we found the density lined up just about exactly with what it really was. Drive gain 4.8%. And so we did some proves. The meter factor 9991 and 0.0002%, 0.02% between runs, where before it was like 6 or 7%. As soon as we were done, it had just 2%, 0.02% between runs. Basically, worked perfect like it should. So we learned from that. Don't put 100% of your faith in the electronic verifications, but especially if there's any kind of another problem. Like if there's indications of a problem, don't trust the electronic verification, because although they work in a lot of cases, on this one they didn't work. The manufacturer told us that the newer version of the software should have picked that up, but the newer version, this is a 2018 meter, so we don't have a lot of meters in the field with the newer version of the software yet. Than that, the newer version came out in 2019, would probably pick that up. But like I said, it's not always there. We did learn something else though at the same site. We got a bonus learning out of this. We're going to put it in now. With its water cut, with the Coriolis meters, they measure the density, and they commonly use that to come up with a water cut percentage. You have your oil is lighter, your water is heavier. If you know the water density, you know the oil density, and you know the actual density, you can determine, like by math, what that water cut is. And at this site, we measured the oil and water density, and we saw there was a big change in water density. The oil density stayed the same, but the water density changed from 1.157 to 1090. So a big change. So 1157 to 1090. And we asked the operators, usually the well density doesn't change, but the operation says, oh no, that's right. We're now having source well mixed in the line down by the well, source water mixed in. So this is going to be our new density. And so we entered that new water density, the measured density, and we should not have ever done that. What did we do wrong, I guess, is our question. And what was the effects? And what happens if that fresh water gets shut off or gets more if the well goes off? And so we learned that really quick. It was perfect when we were there. It had the exact water cut. We tested the water cut. But as soon as there was any change in the fresh water going in with the produced water, it didn't work. And what we learned is when you're using density to determine water cut, you can have water and oil, and they need known densities. If you have 3 products like fresh water, produced water, and oil, you don't know what that water density is. And so you really don't know your final density. So if you're using density, you have to have 2 products and know the densities. So we learned something from that as well. Okay, another one, Coriolis. There was about 6% variance between runs on an inlet separator. This is the an F series 1-inch meter it was on, and we found that the level control, it was on this type of meter. We found that it was set up for throttling action on a control valve, and anytime the flow would go slower than around 20 cubes a day, the factor would drop way below 1, and it showed very inconsistent repeatability. When it was flowing above 20 cubes a day, it was accurate and repeatable. The well made like in the range of 60 cubes a day, so a lot of the time it was above that, but it would come in slugs. So a lot of the time it would be accurate, and then some of the times very inaccurate. Here's a proof that we did, and you can see the numbers. The meter factor went from about 1.003 to 0.94. It's about 6% between runs, and it was directly related to the flow rate we found. That was one of those duh moments that you sometimes have. We found that the accurate range in the different meters, they have different flow ranges. That was in this one, and really the accurate and the recommended, when it gets the accurate in this should have been from 10 cubes a day up, and we saw this inaccuracy starting about 20 cubes per day. But every meter's got an accurate flow range, and if it's not in that accurate flow range, they don't always work accurately. There's a really neat chart that we have on our website. You can download a little PDF of flow ranges of a lot of different meters. So I'll encourage you guys to get that from the website after. meas.ca is the shortest way to get there. Okay, next, we found this variance. We changed the controller to a snap acting controller, and then when we changed that, the flow rate was maintained in the more accurate range. As soon as we changed the controller, nothing else, we got then 4 runs. They were all dumping at a consistent range, and you can see a 0.04% repeatability between runs as soon as it was changed. So that was one of our things that we were able to learn as well. You need a snap acting controller to keep the on your control valve to keep consistent. The meter needs to be in the recommended range and the consistent flow rate. This one is right in the directive. So if you follow directive 17 of the AER, you'll see that your snapback control valve needs to be downstream of your meter anytime you're measuring through that meter. So it is right in the directive as well. But you quite often see them set up as throttling, especially on new systems that haven't been changed, haven't had a problem. And really, if it throttles above the minimum, it probably works pretty well. But if it drops below that minimum, it doesn't work. Okay, next one, turbine meters. You guys all have seen turbine meters. It's a very common meter. It's on a lot of different things. These were 2 meters, opposite ends of about a half-mile water line. Freshwater line flowing through both meters, the same water. And they were identical meters, just absolutely identical meters. What we found on the 2 meters, they have a recommended rate 11 to 80, and we found most of the time it was on a throttling because it was fresh water. They didn't want to shut it off and have it stop ever for the chance of freezing, so it was throttling. But most of the time it was about 18 cubes a day. Occasionally would drip to about 10 cubic meters per day flow rate. And these meters, they're water meters. There's no easy way to field prove them, so they were taken out and bench proved. And it looked from all indications that they should read the same. Remember, there was a 7% difference between them. So we thought, what are the possibilities? What could we look for here? How come there's this big difference between the meters? And so we asked ourselves, are they programmed correctly? And there's a totalizer on each end, the identical totalizers, both programmed, correct K factor, everything looked good. We couldn't see anything in the totalizers that would be incorrect. Were the meters actually going under range and not turning? Well, it didn't seem like it. They never went below 10 cubes a day. The one totalizer was the one that they would normally look at because it was at the end that they would hang out at, and they could see it would never drop below 10 a day. Usually it was 18 and sometimes go 10. And the 3/4 inch meters have a flow rate 10 is the minimum, so they were above the minimum. It should be working good. Could there be some kind of a damaged pickup probe, the magnetic pickup probe? We proved these meters. We switched probes. We proved them again. We put meter parts from one to the other, improved it. We found both the meters appeared, they were consistent. They were hardwired in, so totalizers were never brought to a meter shop. This was done at our shop, was done at another shop prior, and because the totalizers were hardwired into their SCADA system, they never did come with it. So then we did some more troubleshooting. We verified the pulse output voltage from the meter. So right on the magnetic pickup probe, you can read that output voltage. On this one, normal flow rate 18 cubes a day. They had different voltages coming out of them. One was 11 millivolts, the other was 17 millivolts. We tested them both and found that they would count down to the 9 cubic meters per day for both. When they were on our shop prover, we could go slower. You know, they both count fine to 9 cubic meters. So that's below what they would ever normally see in the field. And then we dug out the specifications and we found the trigger voltage for this particular type of totalizer they had was at 10 millivolts. And it's like most totalizers you see will have a trigger voltage you can change. Sometimes it's selectable. You know, new flows would be selectable, high sensitivity, low sensitivity. The low sensitivity is usually about 4 millivolts or 3 millivolts, somewhere's in there. Some are 2 millivolt trigger voltages. 10 millivolt is very high trigger voltage. And so what we found is these ones would count good, but the one that had the lower millivolt output at 18 would actually quit counting just below 18. It would drop about 17 cubes a day. It would get to the 10 millivolt and it wouldn't count. What we did for resolution is we found they're 3/4 inch turbine meters, and on this particular brand, a 3/4 inch is really a 1/2 inch. Most turbine meters are like that. 3/4 and 1/2 are the same body with a different kit. So we were just able to put in 1/2 inch repair kits in these. We did some additional proofs. We found with the 1/2 inch kits, they spin a lot quicker. It makes an output of 26 to 28 millivolts, and they counted right down to a rate of 4 cubic meters per day, where the 9-inch kits stopped at 9 cubes a day. These counted right down to 4 cubic meters a day. They counted all the way through. And so what we learned is the shop didn't get the whole story here. There were different totalizers out in the field than we have in the shop. And just about every, like the shops will use different ones to count the pulses off the meter. Some use different, but most of them in the shop, they usually count similar to the ones in the field, but these ones in the field were different. And so because we didn't have the actual ones, that's why us and the other proving company as well that did it didn't notice that right away. They're water meters and the totalizers connected to SCADA, so the totalizers were never brought with the meters when they come into the shop. The meter does need to be in the recommended range, which they were, but because the totalizers wouldn't count at the bottom, it didn't actually work. So there is so that's what we learned about our totalizers. Okay, just welcome. There's someone else joining us here as well. So okay, Coriolis line balance meter. There's this line balance meter. It's on one end of an NGL line. It's for line balance only. And the other end of the delivery, the other end has a delivery point meter that it's compared to. And this meter, it was installed new, and it wasn't proven it was installed. It's just line balance, but they put it in everything. They used meter factor of 1 and it balanced. The density was 505 grams per liter. The second year it was proved with a bidirectional ball prover. They used the settings of 500,000 pulse per cubic meter, which should have probably thrown up some red flags because just about always you said 100,000, not 500,000. But it worked fairly close. The meter factor had shifted about 3% after the first proof. There's no density, so we didn't know how much we don't know what the density really was in that year. The second year they came to prove it again. They used the same prover, the same settings, the same bidirectional ball prover. It shifted another just about 3% to give a new meter factor about 1.06. And once they entered that new meter factor, their line balance was out of balance because there was so much differential. It was 6% out basically, and its line balance meter, once they're over 5%, it triggers alarms nonstop. So this meter, if you can see it, the flow comes out of a line down here through the meter. Their Coriolis is on there. Down the end, it went through our meter in the middle of the plant and then out. And so that's the way we, excuse me. So that's the way we tied into this meter, and it worked very well as far as our proof. When we did it, we proved the meter because we're worrying about, that there was issues on this meter. So we wanted to make sure that we could prove it. We took our portable in and we proved it 3 different ways. We proved it frequency to volume, as the same as the bidirectional ball prover had been doing. Then we proved it volume to volume, and we also proved it mass to mass. And what we found is when we proved frequency to volume, as it was previously done, we got a similar to the, basically a similar K factor to what the ball prover had, the 1.06 number. Our density was 480 grams per liter. When we proved it volume to volume or mass to mass, we got the same meter factor of 1.0083. So mass to mass and volume to volume were the same, but frequency to volume was quite different. Sometimes when you go through the airport, they ask you a question which always seems to not make sense. But did anyone put anything in your luggage without your knowledge? Well, if it was without my knowledge, how would I know about it? Well, in here we found that sometimes putting things in without your knowledge also happens. There's a frequency output that's used for proving. Normally it's set that at 1,000. It was set at 1,000 pulse per kilogram. Normally it's set on pulses per cubic meter, 100,000 pulses per cubic meter. The density was fixed in their system, 506 grams per liter, which is what it was when it was originally programmed. And year 1, that was their density. The flowing density changed over time as their process changed, and really as it got better, they were able to get more and more liquids out of the gas stream, and their density went down to a 480. And so that change from the 506 to the 480 is basically the exact same change we saw in the difference in the meter factor. Sometimes we call this an ID10T programmer. There is it was really confusing the way that it uses it in this. The change in the meter factor is basically was explained by the difference in K factors. Really, they were using a K factor of 500,000, and that wasn't what was really there. They thought it was 500,000 pulse per cubic meter. Really, it was giving 1,000 per kilogram. When it first started and the density was really close to 0.500, or just a little higher, the 500,000 worked. As the density shifted, their number didn't work. That was low due to the frequency output set to mass, not volume. Once the operations were able to enter the new meter factor, everything again was in balance. It dropped it to 1.0083, 1.0064. It dropped it, everything again balanced, and they were all happy. So what did we learn at this one? We learned the programming and some of the different parts of the system might not always be what's expected. Your Coriolis transmitter has factors entered in several places, and here it's in a transmitter, in a rock, in an HMI, and they all need to be correct so that it works. So the transmitters need to have the right factor in the different places. And anyhow, this one here had it in 3 different places, and it didn't use a normal. Typically, they'll use a pulse input or read over the RS-485 on these right to the transmitter. This used a pulse to convert the mass, and then a factor entered for the density. And so it was a very different way of entering the stuff, which made it very, very confusing. And that's really why there was an issue here. It was just very difficult to follow. Okay, just a couple more things. There's these new Superskids, and I must have thought that you guys could really, really small writing when I wrote this one here, but they have this Coriolis meter. The Superskids have a 2-inch Coriolis on these new on new high volume wells that we are looking after. And the 2-inch F series, we found the densities were reading consistently low, making the volume read high and the meter factor be less than 1 by that same amount. On the 1-inch F series, which some of them use, the readings were accurate, the density was accurate, the volume factors were really close to 1. And what we found is there's a process effect on the density of the F200 meters, and not on the F100 or the different series of these. Just it only affects the 2-inch meters, but it's got a different amount, 0.0003 kilograms per psi, which it makes a 3% error at 7,000 kPa, around 1,000 pounds, and that's what these were running. And what it does is the density, if you do the math, instead of where it should be reading a 675 density, it comes in at a 645 density. And so in effect, it makes these meters read out by 3% anytime that they're at that pressure. So the new ones were right out by that same pressure. So we learned on this, when the meters were trending all one way, we had to ask why. And in this case, it was right in the manual. It tells you exactly the amount that it's out, and we could calculate, and it was exact what we were seeing in the field. So sometimes if all your meters are trending a certain way, and once we notice the 2-inch ones read all low, the 1-inch ones read right, what are we doing different? How come we're not proving these? And we use the same proving system and the same stuff, and all of them goes one way. You sometimes need to research why you're doing it all the same direction. Okay, somewhere's now. Here's my note here. Oh, my joke for the day, my second joke. What do you call a bee that can't make up its mind? That would be a maybe. I know, I can hear the groanings. Okay, control valve passing. We're going to talk about control valves here because really it's the most frequent issue we find. If we go out in the field, somewhere's around 1 in 10 we find passing when you check them. Every meter around has a minimum flow rate, which we've sort of talked about already, and valves passing are normally way below the minimum flow rate. And they're often, when they pass, it's assumed to be a production dropping over time. If it gets missed, they can go a long time, and there's quite a few of these that are on fairly low, like the ones we've seen lately. The wells make 2.5, 3 cubes a day. A lot of the wells that we're at for these particular ones we've been finding. And if it passes, if you have like wells making 3 cubes a day or 2.5 cubes a day, and your valve is passing a cube a day, you're below the minimum of the 2 cubes, and you don't have to field prove them. You can now bench prove them. And so these, when they get taken out and bench proved, usually the meters don't get, or the valves don't get checked at that time. And so anyhow, it's very easy to miss those. And so what we need to do is check that they hold 100% of the time. A passing dump valve, it can easily, if you have a turbine meter on, a 1-inch turbine, it needs to go about 10 cubes a day without turning, or until the meter starts to turn. And so if it makes less than that, you're not going to notice it on the meter turning. And if you are not passing very much, if you pass like a 1/2 cube a day or 1 cube a day or 1/4 cube a day, as long as your well's making more than that, it doesn't lower the separator level. So it's very easy to go a long time and not get noticed. It's not that hard to check them. There's different ways. We usually will just put on the where are we at here? On the upstream side of the dump valve, we'll put a gauge and close the block valve and see if it holds pressure. If it drops, it's fairly easy to check though with a digital gauge, one way or the other, but you want to make sure they hold 100%. And so that's the summary. Got some of the things that we've learned so far out of this today. Settings at the very end of their range. If you have a setting like it goes from 0 to 8% and you're at 8%, question the settings that are right at the very end of the range. There's often errors because where we had a 0 to 8%, it should have really been 10%, but the range didn't go high enough. Secondly, if you're using a density to determine a water cut, you can't have 3 products in the mix. You have to have 2 products in the mix. If there's a third product using that density to determine the water cut, doesn't work well. it's also the same if you have different densities of oil that can vary going into it. If you don't know the density of the oil and then the water, using the density to determine water cut does not work well. Use snapback to control valves to keep consistent. It makes consistent flow rate through the meter, and it's consistent and repeatable each time. The meter dumps at a recommended rate. Every meter has a rate that it's like a maximum and a minimum, and there's a really easy to use cheat sheet on our website that you can download a PDF copy. So I would suggest you guys do that. And then it's got a lot of the common meters. It doesn't have every meter, but it does have the majority of the meters listed on there. And so you can see what the flow rates are that they should be. And what you want on the meter rate, I get this question over and over, but it's the instantaneous dumping rate is what we're worried about. I'm not worried that the well makes 3 cubes a day and it's got a meter that has to dump 27 cubes a day. We're worried about the rate when it's actually dumping. It should be over the meter rate, not when it stops. So it can dump 27 cubes a day for 10 seconds and then be stopped for 10 minutes. That's just fine. It's the meter recommended rate. And then shop proofs don't get the whole story. The things where the totalizers were different in the field than they were in the shop, and normally that wouldn't make any issue, but occasionally it does, because sometimes there are different totalizer that works different than most of the others you see. So sometimes that does make a difference. And then a few more things. Programming different than what's expected. For example, the Coriolis, it's programmed in pulses per cubic, or pulses per kilogram instead of pulses per volume unit. Things like that are different than expected. In a Coriolis transmitter, there's several different places you can have meter factors. They all need to be correct in all the different places. And typically we'll put a tag on and say right on the tag where it's programmed. It's not wrong to program it in any of the different places. The transmitter or the rock or the HMI, if you do it in the rock, it keeps track as the meter factor, and there's a history. The others don't have histories, but for different reasons, you could make a good case for programming it any of the several places in the HMI or the rock or transmitter. But usually you put the meter factor in one spot and everything else has a factor of 1.0. And if you record on a tag and put it with the meter, the next person that comes along will know where to program it. So it doesn't get programmed wrong. It doesn't get programmed in the wrong spot. And then finally, passing dump valves. They cause the most field measurement errors in our experience. Like I say, about 1 in 10 of the field proofs we do, we'll find that when we get looking. So watch your dump valves, verify your dump valves. If you're doing field proofs, you'll probably see that when you're there. You should check it. If you're pulling the meters out and doing a shop proof, they need to be checked as we go. And you'll find those things. So questions? Any questions from anybody? You have to unmute your mic or else send a text, but I'm open for talking to any questions there. Any of the BCI guys have a question? I'm not hearing any questions so far. Oh, there we go.
No, it was very informative, Jerry. I think we'll probably have 10 questions once we get off of here, but nothing right now.
We're kind of shy.
I'm sure everyone is. Okay. Okay, no problem. I put one question here, like someone might ask, why do we do 14 checks before we do a proof? I don't know if some of you guys notice you have like nice proof reports. Some people like their proof reports to be put on Protrend report, and we always do ours before. That's because we do these checks on ours that are, it forces us to do 14 different checks before the proof, and we find some of these issues. So sometimes checking those things are good. Let's see. I'm going to point you guys to our website, www.mes.ca, if you want a meter programming sheet. We also have some stuff from the directive, a few cheat sheets there that you can download and some valuable resources. And if any of you'd like, if you found this informative, if you want to send me an email, that would be great. We're always looking for testimonials or things if people have said, yeah, this was useful, so we can get other people to listen and maybe teach someone else something. So that would be good. I learned a thing this with the coronavirus and marriage. It's putting a lot of stress on marriage. And one of our friends was telling us, one of my friends was telling me, if you're married and you're working from home from this, you're either going to be having kids in 9 months or there's going to be a murder in your house. But I learned something from Joel Osteen. So I'll leave you one last comment. He says, do you want to be right or do you want to have peace? Sometimes you can't have both. And I think in our marriages, when everyone's stuck in the house more than you're used to, that's something we have to sometimes think about and accept. You can be right or you can have peace, but you can't have both. So that's my little bit of advice to leave you with, and we will sign off. Thanks so much, everyone, for joining. It was good to have everyone here.
Thanks, Jerry.
Thanks, Jerry. We appreciate it.
Thanks, Jerry.
Yes. Thanks a lot. You're all welcome. We'll see you.
See you later.